emitter. So the major emitter, got it. On the x-axis, the box plot represents the atmospheric inversions for different period of time. In red, you have the fossil fuel, and in green, you have the lancing. The black horizontal line represents the net CO2 fluxes for the inversion, and the circle represents the mean of the UNFCCC national greenhouse gas inventory data, what countries are reporting to UNFCCC. If you focus on the green part, you can see that there is a striking consistency between the mean for each period of national greenhouse gas inventory carbon sinks and the inversion for all major emitters. Now, this kind of study really paves the way for countries and the global community to improve checks and consistency of national inventory to more accurately reflect global emissions. On this slide, so here on the left-hand side, that's the paper I was mentioning. The figure is from this paper. And the RECAP 2 CCI group has also submitted a paper to reflect some lessons learned from their activity. And the objective was to identify ECVs that they consider key priorities to improve estimates of natural versus anthropogenic greenhouse gas fluxes for comparison and verification of national greenhouse gas budget. So they've made a list of recommendations for the use of top-down and for the use of Earth observation, in top-down inversions estimates. And in principle, some of those recommendations can be addressed by incorporating more Earth observation data into atmospheric inversion. And examples include fluxes from biomass burning. So there we are, biomass. As you probably know, or most of you know, we have a CCI climate change initiative project that focuses on fire. It is led by Emilio Chubieco at the University of Alcalá near Madrid. And it is true that satellites permit to monitor different fire characteristics. We can monitor areas that are dry and prone to wildfire outbreak, actively flaming and smoldering fire, burn area, as well as smoke and trace gas emissions. And here you have a Sentinel-2 images that give you a nice illustration of some of those processes. Several satellite systems are currently available for fire monitoring with different capabilities in terms of spatial resolution, sensitivity, spectral bands, time and frequencies of overpasses. The satellite can measure electromagnetic radiation, the light reflected and the heat emitted from our planet. And we can use different types of instruments, such as visible and infrared detectors. The visible ones can detect smoke plumes from fires, as well as burn scars on the ground. And the thermal infrared one can detect actual hotspots and active fires. And we identify from space areas on the ground that are distinctly hotter than the surrounding, and we can flag them as active fire. And the differences in temperature between the areas that are actively burning with respect to neighbor areas allows the identification and mapping of active fire. So if you put the notion of risk monitoring and risk assessment aside, if we focus on fire in the context of the Paris Agreement for climate, it is because vegetation on land disturbed by wildfire has the potential to release significant greenhouse gas and particulate matter into the atmosphere. It is estimated that about 25 to 35% of greenhouse gas result from biomass burning, and therefore they are considered an important factor in climate change. The Fire CCI project focuses on the key variable burn area using a hybrid approach, combining surface reflectance and thermal anomaly. It has different products at global scale derived from AVHR, MODIS, Sentinel-3, but not only. It has also recently focused on high resolution at regional scale using Sentinel-2 information at 20 meters spatial resolution to develop a small fire database covering sub-Saharan Africa for the year 2016 and 2019. And the results were very, very interesting. On this figure, you have the evolution of the total yearly burn area for different global moderate resolution product. They are the line. And on the top right part, you have two dots, one red and one black, representing the burn area derived from Sentinel-2 data only for sub-Saharan Africa. And you can see that looking at small fire, higher spatial resolution permit to increase a lot the burn area. And it is also very interesting to see this green triangle. This is a new data set from a new methodology. It's a global data set, but this time based on Sentinel-3 synergy data, a combination of SLSTR, SLSTR, and OLCI. And it presents much higher value compared to other global products, such as the one based on MODIS, the green. Yeah, I assume you see my mouse. The blue MODIS product. So as I said earlier, we use a hybrid approach to detect burn area using both thermal anomalies information for hotspots and reflectance value. The Sentinel-based product use VIRS hotspot that has a spatial resolution of 375 meters instead of the MODIS-based product that use its own MODIS hotspot with its 1 kilometer spatial resolution. And this has definitely a major role in detecting more burn area. The Sentinel-3 based dataset also uses the shortwave infrared instead of the near infrared, and there were also some improvement done to the algorithm. So not only the Sentinel-3 based product detect 28% more burn area than the MODIS product, but it also has a better accuracy. It is an improvement in the capacity to detect burn area from medium resolution sensor. The Fire CCI project, phase 2, has kicked off recently in earlier this month, and they have a list of activities, of course, still linked to user involvement and requirement. They will extend the burn area from the Sentinel-3 synergy data. We want to develop a new merged multi-sensor burn area product at a global scale. We will try to do long-term, high-resolution, higher spatial resolution burn area series, combining a Landsat and Sentinel product. And I think that's the most important part of this presentation. We will look at the value of Fire CCI product in fire emission and carbon modeling. Guido van der Werf and his team from the Free University of Amsterdam that were at the beginning of 10 years ago in the project are back in the consortium, and this topic will take off. And I personally believe that if we can combine burn area from the Fire CCI project, biomass, for example, from the CCI biomass project, together with information from the CCI land cover project, like the new map of annual plant functional type, that could help disentangle high and low vegetation in the biomass product. There is something very interesting to do in terms of fire emission. So maybe a note for Martin and from Philippe. Of course, we could wait for the CCI collocation meeting in October to discuss that, or already organize a meeting between the different parties involved, and I will personally favor the latter. Thank you very much, Martin, for having me, and I hope I stick to the 10 minutes. Thank you.